Kia ora. Let's now look at this using the EEC method when we're calculating the solubility of a substance in the presence of a common ion. So we're going to follow the same thing. However, we now have our cation and anion coming from two different sources, of which one of them is already there. So we can't use the shortcut. So the two examples we've already looked at, calculating the solubility product and the solubility of a substance. If we're just talking about dissolving it in pure water, we can use the shortcut of Ks is equal to S squared for an AB salt or 4S cubed for an AB2 or A2B salt. Now we can't, because our ions come from two different sources. So what do we mean by this? So here's a common ion problem. Calculate the concentration of barium ions which will dissolve in 1.00 moles per liter of potassium sulfate. So we've got barium sulfate. So the cation is barium, the anion is sulfate, but we also have a solution of potassium sulfate where we've got a cation of potassium and an anion of sulfate. So our common ion is sulfate. Now, if you're not sure which equation to write, because you've got now potassium sulfate and barium sulfate, always use the one where Ks is given. So write, for that EEC method, the equation, you write the solubility equation for barium sulfate because you were given the Ks for barium sulfate. So one barium sulfate will dissolve to form one barium ion and one sulfate ion. So in the beginning, if you think of a beaker containing a solution of 1 mole per liter of potassium sulfate, and I add some barium sulfate to it, I'll have lots of barium sulfate. I'll have no barium right in the beginning, but I will have sulfate from the potassium sulfate solution, and we know the concentration will be 1 mole per liter. Then it will start dissolving. And so for every one barium sulfate that dissolves, I'm going to form one barium and one sulfate. So if X dissolves, I'll have a bit of a decrease of barium sulfate, solid in the mixture. I'll have X of barium ions dissolving and going into solution, and I will have X of sulfate going into solution. So if I have lots and I subtract some X, it'll still be lots, so we can ignore that. And so we've got X and 1 plus X for our ions. Now we can get into a bit of a tricky math, so we are going to make assumptions. We are going to say, because a Ks is so tiny, very little is going to dissolve. So if I'm going to add 1 plus 0.000000001, if we round it off to 3 significant figures, it's still going to be 1. So we're going to assume that all my sulfate is not going to be 1 plus X, it's going to be simply 1. So remember, EEC equation, expression, now we substitute into the expression. So we know the Ks, we substitute. Barium ions is X, sulfate ions, we've made the assumption. Remember to state the assumption, and that is 1. Now we simply solve for X, and we get a value of 1.5 times 50 times 10 to the minus 9 moles per liter. If we compare this to the solubility in pure water and we use the shortcut equation, you'll notice that the value is quite different. It's quite a bit higher. So in pure water, barium sulfate is a lot more soluble than when we've got a common ion present. Let's do another problem. We've got silver chromate in a 0.1 mole per liter. So again, we've got potassium chromate and silver chromate. Our common ion is the anion chromate. If you don't know what equation to write, remember you look for the Ks and it's silver chromate. So the silver chromate will dissolve to form 2 silver ions and 1 chromate ion. So in the beginning, I'll have lots of silver chromate. Nothing's dissolved yet, so I'll have 0 silver. However, I won't have 0 chromate because I've got chromate from the potassium chromate solution, even though I've got none from the silver chromate. Then the silver chromate starts dissolving, and if X amounts dissolve, I'll have twice the amount of silver and X for chromate. So I'm still going to have lots of silver chromate that's undissolved. I'll have 2X of silver ions, and I'll have 0.1 plus X. And again, we can make an assumption that really the amount of chromate from my silver chromate is so tiny that when I round it off to 3 significant figures, it'll still be 0.1. So when I now write my expression, I will now put in my 2x that's been formed, and I square my 2x. So remember, you've got to look here and substitute into the expression, and then just follow the rules. So chromate is 0.1, silver is 2x squared, and there's my Ks for the silver chromate. So 2x raised to the power of 2 is going to be 4x squared. So I have to get rid of the 0.1. So if it's multiplying on this side, it has to divide on the other side. And so now I first will solve that. Divide it by 4 first before you take the square root. That will minimize errors. And I'll get 2.73 times 10 to the minus 6 moles per liter. If I use the shortcut method, which you can only use in pure water, then you'll see that your solubility is a bit more. It's so our silver chromate is more soluble in pure water because it's 9 times 10 to the minus 5 compared to about 3 times 10 to the minus 6. So this is a smaller value. Let's do one more problem. So we've got calcium fluoride, where we now have a common ion of fluoride. So again, it's the anion, but this time it's 2 fluorides for 1 calcium. So it's an AB2 salt rather than the A2B salt we saw in the previous problem. And the same thing in the beginning, we'll have lots of calcium fluoride because it still hasn't dissolved yet. No calcium because nothing's dissolved. Fluoride, I have got nothing from the calcium fluoride, but I have got from the sodium fluoride because this is a totally soluble solution and it's 0.1 mole per liter. So when it starts dissolving, I'll have X dissolving. So I'm going to have X of calcium because every 1 calcium fluoride makes 1 calcium 2 plus ion in solution. And I'll have twice the concentration from the calcium fluoride of the fluoride. So I can ignore that for calcium fluoride. The calcium ion is X. The fluoride ion is 0.1 plus 2X. But again, I can still make the assumption because my 2X is actually even less. So if I round this off, it's still going to be 0.100. So that makes the maths a lot easier, and I substitute. So I substitute my Ks value. Calcium is X, fluoride is 0.1, and I square that. So if I solve for X, I've got 4.00 times 10 to the minus 11. My 0.1 I have to square. I suggest you do that first before you do the division. So if I square the 0.1, it becomes 0.0100. I should have given more significant figures here. And then I get 4.00 times 10 to the minus 9. And if I did it in pure water, you'll see that the solubility is quite a bit different. This is a lot more soluble in pure water than it is in the presence of a common ion because of this doubling effect of the fluoride. So hopefully you can use this ICE method of think of where are my ions coming from, make the assumption, substitute into the equation, and work it out. Do it stepwise so that you don't make any careless errors. Kia ora.